Hi guys, welcome back to Data Every Day. Today we're looking at a data set of McDonald's menu items, and we're going to try to predict the type of a given item. So we have like breakfast, beef and pork, chicken and fish. There's a bunch of different types of item. We have a bunch of features about each one. So let's go ahead into our notebook, and you can see I have the task for today, given data about McDonald's menu items. Let's try to predict the type of a given item. And we're going to use a TensorFlow artificial neural network with two inputs to make our predictions. So I have some libraries here, NumPy and Pandas for working with the data. For pre-processing, we have a few imports. It's regular expressions, the tokenizer and pad sequences from keras.preprocessing, and the label encoder, standard scaler, and train test split function from sklearn. And like I said, we'll be using TensorFlow for our model. So let's go ahead and load in the data using pandas.readcsv. And we can get the file path right over here, copy that, paste it in, and take a look. Alright, so the reason I say we're going to use two inputs is because I want to use the item name as feature data. The problem is it would be hard to encode this in the same data frame, because the way I would want to feed this in is by using the words as like individual vectors. I want to feed each word in. Now, I could one-hot encode the words, but there's a problem with that. Is that we're going to end up with a lot of columns in that way, because each word has to be represented in a vector whose length is the length of all words. In the one-hot encoding scenario, you'd have a 1 for a given word and zeros for all the other words. But that's a lot of columns. That means we will need, it's a lot of sort of wasted space. That would be a sparse encoding. So what I want to do is a dense encoding, where each word is pointed to a location in vector space, and the way it's encoded is just as a vector in some vector space. And we can use the keras embedding layer to actually learn where to send the word vectors. And so what we're going to do is feed in this column separately from all the other data. Okay, let's get a little information about the dataset. So we can see we have just these three object columns, which we'll have to deal with. The rest is numerical, and we can also see that we have no null values in the dataset. Right, we have 260 total entries, and all of them are non-null. So let's start by encoding the label column. This isn't very difficult. We're just going to use sklearn's label encoder to do this. So first, let's take a look at the unique categories that we have in the category column. So we have breakfast, beef and pork, chicken and fish, salads, snacks and sides, desserts, beverages, coffee and tea, smoothies and shakes. And what I'm going to do is use the label encoder, which we can create a new one, just a label encoder object. And we're going to call label encoder.fitTransform on the category column. And if we look at what that looks like, sorry, I did run both of them. I'll just run this. You can see it's basically going to take each of these categories and encode them to a new value. So you can see, if we want, we can check the label encoder's classes attribute, which will give us the classes in the order that it encoded them. So if we just go and turn that, we enumerate it, and then turn it into a dictionary, we can see, what's wrong here? Oh, hold on, just gotta fix these parentheses. You can see what each one has been mapped to. So breakfast has been mapped to 2, and that's why we have all these 2s right here, because we have all these breakfasts right here. Alright, so that's just an overview of what this does. We're going to actually set this as the new category, and I want to save the label mappings like this, so I'll call that label mappings, and we'll just keep it on the notebook so we can see it. Alright, let's run this. So we have, if we look at the data now the category is in numerical form, and we have the mappings if we ever need to reference it later. Alright, so now let's worry about the name column. Well, I should say item column, this one. So this is where we're going to tokenize each word. And I don't think these, the way it's formatted now, we don't need any like special pre-processing function. We don't need to worry about removing digits or stop words from the input, because these are pretty simple names. And we're not even going to worry about the time dependence of the words. We're just going to basically use the words as features. So we're going to create a tokenizer. And this is from keras.preprocessing. And a tokenizer is just going to take each word in a string. By default, it splits on white space. And it's going to remove any like special characters. There's a series of filters that puts the word through, and it's going to make it lowercase. So it'll sort of clean up the data for us a little. And then it's going to go through and tally up the counts for each unique word and assign them integers based on their frequency. So the most common word will be assigned 1, the second most common word will be assigned 2, and etc. The 0 is reserved for padding, so 0 won't be assigned to any word. And let us okay, so let's create names, which is just going to be a copy of the item column. And we're going to call tokenizer.fitOnTexts to fit the tokenizer to names. After that, we can transform names using tokenizer.texts to sequences. Alright, if we run this, you can see names has now been converted to integers, and tokenizer actually has something called word index that shows us what got mapped to what. So in the case of this, the first one is an Egg McMuffin, and it's been mapped to 8, 52. So 8 must be egg, and 52 must be McMuffin. If we look, 8 is egg, and 52 is McMuffin. So each sequence now represents a item on the menu. Okay, so I'm going to just get a few pieces of information from this. We're going to have the vocab length, which will be the length of our vocabulary, and it's going to be the length of the word index. But we're also going to add 1 to account for the 0. And the reason for that is we're going to pad the sequences with zeros so that they're all the same length. So our vocab length is the length of the word index plus 1. And we're also going to have the max sequence length, which is going to be, alright, it's going to be the maximum, so numpy.max, of the names, but with a lambda function mapped to it. So I'm going to let me do it this way. I'm going to make this lambda function that takes in an x and returns the length of x. So if I apply this lambda function to names, which looks like this, right? Each one of these is going to be turned into the length of itself. So this would become 4, this would become 6, and so on. That way, I can just take the max of that whole column to get the longest sequence in the column. So I'm going to take this and map it to names. So I'm going to map this lambda function to names, and then I'm just going to turn that into a list, and then I'm going to take the max of it. So this will be our maximum sequence length. Alright, and now just print them out. Let's paste this in. Alright, so our maximum sequence length is 9, and our vocabulary length is 155. Okay, so now what's left to do is we're going to pad the sequences. So pad sequences comes from keras.preprocessing.sequence. We're going to pass in names, a max length, which will be our max sequence length, and we're going to specify padding equals post. That will just add the zeros at the end rather than the beginning. And we can take a look at names after that. You can see names went from just sequences to sequences of all the same length. So now all sequences are of length 9, and zeros fill in for the shorter sequences. Alright, and now since we have names, we no longer need the item column, so we're just going to drop it. Data equals data.drop item. Okay. Alright, let's clean up the serving size feature. So if we look at data, we're going to hold on to names for later. We still have it when we need it. But we have we'll notice, well actually let me say, we have this ... here. That means we can't see all the columns. So let's use pandas.set option to turn max columns to none. Now if we reload this, we can see all of them. And you can see that all of our columns are in numerical form, except for serving size. So that's what I'm doing here. So I'm going to try to encode serving size in a way that just is purely numerical. So I think the first thing to do is just take a look at it. So serving size. Let me keep the data down here so we can see it. So let's take a look at what kind of unique values are in serving size. .unique. Okay, so we have, it looks like almost all of the examples have this grams, right? Because like, it seems to be ounces and grams, but then we also have something like this, which is a carton. However, this is in milliliters. So what we're going to do is we're going to try to we're going to give it a number and a unit. And so I also noticed that there's these, which comes in fluid ounces, but contains no grams. So what I'm going to try to do is, it looks like, because there's only 3 possibilities. I'm not going to worry about the ounces. I'm going to focus on grams. We're going to have either a grams measurement, a milliliter measurement, or a fluid ounce measurement. So let's do this. We're going to create these little functions. Get grams, that takes in a serving, which will be something like this, right? We're also going to have get milliliters, and we're going to have get fluid ounces. And I'm going to have at the top here units, which is going to be an empty list. I'm going to add to the units from within the functions. So, okay, how should we do this? So we're going to use regular expressions here. But before I do that, I just want to say, so if we're getting grams, we want to specify that we're using grams. So I'm going to encode 0 as grams. If we have milliliters, I'm going to encode that as a 1. And if we have fluid ounces, I'm going to encode that as a 2. So this will map at the end, units will be filled with the measurements, the units. How do I don't know. I can't really explain. if we're going to call this, we're going to call one of these on each example, and then depending on which one we called, units is going to get a value that corresponds to the unit. Alright, and then we're going to return a regular expression. So why don't I open up regex101.com, which is a fantastic way to test regular expressions. We're going to grab one of these strings, paste it in, and we're going to try to use a regular expression that's going to capture this number. So because it's in parentheses, I'm going to, how do I say it? Okay. We're going to use a positive look behind, which is basically, we have this capturing group, and we want to say, okay, so question mark less than equals is a positive look behind. And what that means is we can specify something after that that will come before what we're trying to capture. So in this case, it's going to be a parenthesis. So you can see, let's say over here, assert that the regex below. Okay, so what I'm trying to say is that we have this parenthesis that we captured here, and we're saying look at what comes after it. And what I want to see that comes after it is any digit characters, any number of times. And so that's going to capture what we want. I don't think there's any decimals, right, in the grams. Not that I could see. They all look like integers. So yeah, it looks like maybe the only decimal values are in the ounces, but we're not going to use that. So we don't have to worry about it. And we're going to grab this regular expression, and we're going to use it here. So I'll keep it for a second. So regular expressions.search will search the string that we specify for a given regular expression. The regular expression we want to use is this one, and the string we want to search is serving. Then to get the results, we'll say group of 0, and then we want to turn this into an integer. So when we have a grams value, we're going to call this to get the grams as an integer. Alright, for milliliters, it's very similar. In fact, it's exactly the same, right? Because in the milliliter example, we also have the first number inside a parenthesis. And for the last one, fluid ounces, we actually just want the first number that appears. So for that, all we have to do is assert beginning of the line, and then digit characters. However, here we actually need to include the period as well. So we're going to put it in a group like this, and include periods as well. And this will grab the first number. Okay, since this needs to be a float, we'll make this a float as well. Infy.float, infy.float, and then here's the new regex we're using. Let's just put that inside there. Okay, so these are our three functions we're going to use. And okay, so data sub serving size is right. This is our here it is. We're going to apply a lambda function that takes a serving, which will be one of these things, and it's going to return get grams of serving if space g is in serving. So that means it's going to search and find if space g is in it. And it doesn't, there's no other place in here, I believe, where we have that problem, but I think actually space g parenthesis, that will ensure that we're dealing with just the grams examples. So else, if So if, let's see, space ml, parenthesis, we're doing milliliters here, then we're going to get ml of serving. I realize I didn't close this. Sorry. And else, we're going to use get fluid ounces of serving. Okay. So this way we're calling one of these three based on if we have grams, milliliters, or fluid ounces. And I think this should work. At the end of this, after we've called this on each example, units will be filled. So what I'll say is create this new column, serving units, which will just be units. I must have messed this up. Oh, can we not use... Yeah, give me 1 second. Okay, so I just realized we can't do else if in a single line like this, which in fact it's actually really messy. I wouldn't want to do it anyway. So what we're going to do instead is create this new function that I made, get units, which is just going to do the else if on multiple lines. So we takes in some serving, and if grams is in serving, we'll use get grams. If ml is in serving, we'll use get ml, and otherwise we'll get fluid ounces. So what we can do then is apply get units. So this will apply it to each serving. And I think this should work. If I put this up here, run this again. Why is this not? Invalid syntax. 1 second. Oh, of course. I forgot it's elif. Alright, elif. There we go. Okay, let's take a look. I think this should have solved it. No, it did not. Oh, it's because I didn't set it equal. Okay. Alright, there we go. Alright, we have numerical values and serving size and the serving units here. If I take a look at the units, you can see that it has zeros at the front and then twos, and then there should be some ones in here as well. Only a few though. I think there was only like 1 or 2. Oh, there they are. These are the milliliter ones. Okay, fantastic. So that's what we have on the side, and then we have it in a numerical form here. Alright, that was annoying, but we took care of that. All of our data is numerical now, so let's split and scale it. Splitting / scaling. Okay, I'm going to split it into x and y. Y is what we're trying to predict, which will just be the category column. So I'll make a deep copy of that. And then x is going to be everything except the category column. No, actually it's data.drop, category, axis 1, and we'll make a copy of that as well. Alright, then we'll create a standard scalar from sklearn, and this is going to give each column mean 0 and univariance. So x equals scalar dot fit transform x. That's going to allow each column to take on a similar range of values. Alright, and then we're going to perform a train test split, but we have to remember to split our names as well. So names is these sequences that we got before. So names, we'll call it names train, names test, x train, x test. So x is our other features other than names, and then y train, y test. Is going to be train test split of names, x, and y. And we'll give it a train size of 70%. And we can begin modeling. Okay, so I'm going to just get the number of classes. So num classes is going to be the length of the unique values in y. And let's just print it out. Then we're going to get the feature length, the length of the vector of the feature vector for names. So name feature length is name. This is going to be names.shape1. So this is number of columns in names. Basically, how long is each name? And we can print out the result of that as well. And then we're going to get the other feature length, which is the number of columns in x. So x.shape sub1. And we can print that out as well. Alright, so we have 9 classes or categories that we're trying to predict. 9 words in each name, and 23 features in the remaining features. I just realized I should probably one-hot encode the units. Currently it's as an ordinal variable, and it's not ideal because 0, 1, 2, it's saying that 2 is greater than 1 and it's greater than 0, which doesn't make sense. We're not trying to say to the model that, for example, fluid ounces are greater than grams. So let's actually just quickly one-hot encode serving size. So I'll just we'll create, let's see, I guess I'll just make a function, one-hot encode. It's going to take in a data frame, a column, and a prefix. And data sub, we'll just create a copy of the data frame to start. And we'll create some dummies, pandas.getDummies. This is for df sub column. We'll include the prefix of our choice. Then we'll concatenate the dummies onto the end of the data frame. And we'll drop the original column. That's it. Return df. Alright, so what to say is data equals one-hot encode data serving units, and the prefix will be unit. Okay, so now at the end we have units 0, units 1, units 2. Much better way of representing that. So now this, alright, we'll just run these again, and then, okay, I'll just run them from the beginning. Now we have 25 features. Okay, so let's start building our model. We're going to separate it into 3 parts, I guess. Name features, other features, and combine. Alright, and then we'll create the model. Alright, so for the name features, we're going to create an input. We'll call it name input. tf.keras.input. And the shape here is going to be name feature length. So a vector of length, name feature length. And let's give it a name. So name input. Okay, now we'll embed it. So this is what I was saying before. We're going to embed each word in the sequence as a vector in a high-dimensional vector space of our choosing. So this is tf.keras.layers.embedding, and where the words are going to go in the vector space is going to be learned by the model. So our input dimension is going to be basically like a one-hot encoding version of each word. So the dimension of that will be the size of our vocabulary, which we got earlier with vocab length. The output dimension is going to be of our choosing. Let's choose 64. And the input length is going to be name feature length. So that'll be 9. The length of each input, each sequence. So we're taking in basically we're taking in a vector, basically a one-hot vector of each word, and we're outputting a sparse vector, and we're outputting a dense vector in 64-dimensional space. And the model will learn where to send it, so that it'll sort of group them together in a way that's meaningful to the model. And we'll pass a name input, and then we'll flatten. Actually, let me just name this real quick. Name embedding. Okay, now we'll flatten it. Name flatten is going to be a flatten layer. tf.keras.layers.flatten. Give that a name. Name flatten. And we're going to pass in name embedding. Okay, now we can do the other features. So I'm going to create another input, other input, tf.keras.input. The shape here is going to be of length other feature length. Yeah, okay. And we're going to give that a name as well. Other input. Then we're going, for this one, we're just going to run it through two dense layers. So dense 1 and dense 2. They're both going to be the same, so tf.keras.layers.dense, 64 activations, and a ReLU activation function. And we're going to pass in, to the top, we'll pass in other input. And to the bottom, the second one, we're going to pass in dense 1. And why don't I just give these some names as well. Okay. So now we're going to concatenate the two results from each input. So from here we have name flatten, and here we have dense 2 as our outputs. So concat is going to be tf.keras.layers.concatenate. That's going to concatenate name flatten, which came from the names, and dense 2, which came from the other features. We'll give that a name as well. Concatenate. Okay. Now we're going to output. We're going to create our outputs, which will be the softmax activated results from the concatenation. So this will be dense layer, layers.dense, and we'll use num classes activations. So it's a probability estimate for each class, and an activation softmax to give us those probabilities. Let's also name this output layer. Alright, we'll pass in concat to that one. Okay, so now we can create our model. So model equals tf.keras.model. The inputs are going to be name input and other input, and the outputs are going to be outputs. Alright, now let's print a summary of the model. And we'll also create a graph of it with tf.keras.utils.plotModel. Alright, so here's the summary. You can see we have weights we're going to train on the embedding layer, dense 1 layer, and dense 2 layer. And then over here we have the sort of a graph of what's going on. We have an input for the names, an input for the other features. The names get embedded and flattened, and the other features go through two dense layers. The results get concatenated together, and then we have final probability estimates for the output. Alright, so now we can train. So I'm going to give it a batch size of 32, and we'll train for 100 epochs because I'm going to use a callback function that will keep it from overfitting over time. Then we'll compile. Give it an atom optimizer. Our loss will be sparse categorical cross entropy. And our metrics, we'll just use accuracy. Okay. Then our history will be where we store the model fit history. And we're going to train it on 2 inputs, which will be names train, x train from our split earlier, and the outputs it's comparing to is y train. Let's give it some validation data, have a split of 20%, and then we'll pass in the batch size and epochs that we specified above. Alright. We'll also give it that callback function I was talking about, which will be tf.keras.callbacks dot reduce learning rate on plateau. Alright, so that every time it sees the loss stops improving, it's going to reduce the learning rate so as to converge. Prevent us from overfitting over time. Alright, let's train it. And let's get our results. Not too much data, so it's going pretty quickly. Results we can store. It's going to be model.evaluate, and we're passing in names test and x test as our inputs. We're comparing to y test, and we'll turn off verbose mode. Alright, then we'll print out the results. Model accuracy. And we'll just return the accuracy value, which will be indexed at 1. And we got 96% accuracy in our model. It's pretty good. So this was just a sort of a demonstration of how to use sequence data in addition to other feature data. And I hope that is helpful. That will conclude today's video. Thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. So I'll see you guys tomorrow. Have a fantastic day.